Good morning, everyone. Annyeonghaseyo, and I'm very sorry, this is about all I can tell in Korean, so the rest of my talk will be in English. Thank you all very much for joining. It's my very first time at Day2. I'm very excited and very thankful to the organizers for giving me the opportunity to talk to you. My name is Florent Perronin. I'm with Naval Labs Europe in Grenoble, France, where it's currently approximately 3 a.m. So I'm very sorry if I'm not functioning at my fullest capacities. I hope you'll forgive me. My role at Naval Labs Europe involves the coordination of our scientific and engineering capabilities. We have 8 main competencies, including machine learning and optimization, natural language processing, computer vision, data and process modeling, edge computing, geospatial data analysis. We have software platforms, and also, last but not least, ethnography. So today I will be talking about a topic which is very dear to my heart and which I have been pursuing for many years, both with collaborators at Naval Labs Europe, or NLE for short, and with external collaborators, which is large-scale search. And although I will be focusing on indexing of visual data, and especially images, actually what I will be talking about is very generic and can be applied to other types of data, including, of course, video, but also sound, text, etc. So here is a problem we will be discussing for the next 40 minutes or so. We are given a query, and we want to find the closest match or the closest matches in a very large database of what I will be calling entities. As I mentioned, these entities can be images, videos, texts, blogs, users, etc. Let me mention a few possible example applications. If the problem we are trying to solve is video copy detection, then the query is a video, and the database contains videos, of course. If the problem is blog recommendation, then the query is a user, and then the database contains all the possible blogs, and you're trying to match the blog with the user. Similarly, if your problem is ad placement, then your query is a user, and the database contains the ads. What all these problems have in common is the fact that they are very large scale in nature, and the database might contain billions of items, if not more. So here is a bit of a more detailed view. We're provided with a database, in this case of images. Typically during an offline stage, we compute a set of descriptors for these images, which we subsequently store in a database. Typically, we want this database to lie in the RAM of the machines for speed, because of speed constraints, because if you put it on the disk, then typically the search phase will be very slow. Then when you're provided with a query, you compute similar descriptors, which will be denoted X in this case, and here you perform some sort of comparison. Here. And our visual signatures, our visual descriptors, we want them, of course, to be compact, because the more compact they are, the more you can fit into the RAM of a single machine. We want them to be fast to compute, of course, but also fast to compare. And we want them to be accurate in the sense that we want them to faithfully represent the content of our images. So typically our image signatures, our image descriptors, to compute them, you have 2 steps. The first step is an embedding step, which involves projecting the data into a common Euclidean space, so that, like similar concepts are clustered together in this space. For instance, we would like the concept of a cat, the images of cats and videos of cats to be clustered together in this space. while we would like the concept of dog, images of dog, and videos of dog to be clustered together. Okay? And this space, typically, to give a rough estimate, will contain from a few hundred to a few thousand of dimensions. And then in a second step, you would typically compress your data into like an even smaller signature. In what follows during this talk, I will take the first part, the embedding part, for granted. I will assume that this is provided to me by some experts. For instance, in the case of images, this will be, for instance, CNN descriptors. In the case of text, my descriptors or text signatures, they might be provided by an LSTM. What I will really focus on is, once I'm provided with this high-dimensional representation, how can I compress them further? So here is the content of my talk. First, I will provide a bit of background for those of you who are not necessarily familiar with the field of data compression, and I will review the two main techniques to compress data. Then I will discuss the approach that we proposed, which combines the best of the existing techniques. And finally, I will show an application of our very large-scale indexing techniques to the problem of KNN graph construction. So first, let me give you a bit of background about the two main families of techniques that exist for data compression. The first family of techniques are binary code techniques. The idea is to design or to learn a function that maps your original space, here on the left, into a compact Hamming space. So a Hamming space is a binary space. So basically what you're trying to do is to project each point in the original space onto the vertices of a hypercube. And the goal is to ensure that the neighbors with respect to the distance in this space reflect neighbors in the original space. So typically, the distance that you will use in the binary space is a Hamming distance, or the Hamming similarity, which computes the number of similar bits between the two representations. The advantages is, of course, the fact that this provides for a compact descriptors. If you're projecting, for instance, let's say, into 128 dimensions, you will have a 16 bytes descriptors. And also the distance is very fast to compute. This is because the Hamming distance can be computed extremely efficiently with instructions such as SSC instructions. Indeed, your Hamming distance can be computed with operations such as XOR and popcount. Maybe the best known example of a binary encoding technique is LSH, for local sensitivity hashing, which involves random projection of your data onto Gaussian random dimension, and then some thresholding. If, for instance, your projection exceeds 0, then you can set the bit to 1, and if it's below or equal to 0, you set the bit to 0. And the good thing is that, as shown by Sharika and colleagues in 2002, actually, you have some strong guarantees with such an approach, and especially the fact that the Hamming distance will give an estimator of the cosine distance. The more projections you have, the higher the dimensionality of the output space, the better is the estimation of the cosine distance. And LSH is just one example. There are many more recent techniques, especially techniques which rely on the distribution of the data, such as ITQ. I'll come back to it a bit later. One obvious limitation of binary distances is the fact that actually you constrain your points to be on the vertices of this hypercube, which is a very strong and hard constraint. So a second class of technique is, and a more recent one, is a product quantization introduced by Jegu Hervé Gégaud and colleagues at INRIA. It's a very, very different technique. What you do is given an input vector which will denote y. First, you cut it into small subvectors. Let's say, for instance, subvectors of 8 dimensions, as is typical, so that if you have, like a 32-dimensional input, you will have 4 8-dimensional subvectors, y1, y2, y3, y4. And then what you do is for each subvector, you learn a quantizer. For instance, using a clustering algorithm such as k-means, and you replace or you encode the subvector by the index of the closest centroid. Okay? So for instance, if I have 256 centroids, I can encode the subvector on 8 bits. And so you can estimate the distance between, like query X and a database vector Y as a sum of the distances between the subvectors, which can be approximated by the sum of the distances between the query subvector and the quantized database item. Note here that we don't need to quantize actually the query itself, which results in higher accuracy. So binary codes and PQ type of techniques have been seen as competing methods in the literature. They have different advantages and disadvantages. One advantage of binary code is that the comparison is context-free, meaning that to compare 2 vectors, you only need these 2 vectors. While in the case of PQ, you need quantizer centroids. This has a direct impact, which is the fact that in the case of binary codes, comparisons are extremely efficient, because of the possible use of instruction, such as the one I mentioned, like SSE instruction. So here, for instance, I think these numbers are provided, like for a single CPU with 128 bits signature, you can do on the order of 1 billion comparisons per second for the same size of signature, like 128 bits. Then here with PQ, you can do, maybe 1/8 of the same number of comparisons. And this is because you have to access lookup tables, and this is much less efficient than SSE instructions. So on the other hand, so these numbers are provided in a benchmark I will talk more about later. For the same number of bits, the precision of binary codes is much lower than the precision of PQ codes. So basically, you have, like for a number of bits, the choice between, like fast binary techniques which provide lower accuracy or slower techniques which provide higher accuracy. And the question we're asking in this work is whether we can get the best of both worlds. And this is exactly what we proposed in this work, which was just published last year, together with 2 ex-colleagues of mine at Facebook Air Research, Matthijs Does and Hervé Gégaud. So first, let me go with you through a very simple and naive approach, to solve the previous problem. What we could do in a very naive way is encode all our database items with both binary and PQ codes. Okay? So that when I'm provided with a new query vector X, I encode it in a binary fashion. And then when I loop over all my database items, for database item I get the binary code. And then if the Hamming distance between the query and the database item is below a threshold, then in this case, I can compute the PQ code and perform the PQ distance. Okay? So this 2-stage comparison speeds up the process, a lot, because the first fast Hamming distance acts as a filtering stage. And then we do the costly comparison with PQ only for a subset of the items that pass the test. Okay? So indeed, that would speed up quite a lot our procedure, but this would also increase the memory of requirements for database by a factor of 2, because we need to encode everything with binary items and with the binary technique and the PQ technique. And if you have a very large data set, duplicating the size of your data set is simply not possible. So the question we ask is, could we use the same codes for both the Hamming and PQ distances? And that's exactly what we'll do with Polysemous code. So the idea of Polysemous code was directly inspired by work in channel optimized vector quantizers. When you want to encode and transmit a signal, you have two possible sources of distortion. The first one, of course, occurs during the coding itself. So you have your vector x, you encode it, for instance, in a binary or in a PQ fashion, and this is a source of distortion. But then you transmit it over a channel, and because there might be noise, actually, you might, for instance, flip some bits, okay? And what we want to do is minimize overall distortion, meaning the distortion that is incurred by the lossy compression stage, but also the distortion which is incurred by possible noise, okay? And in the signal processing literature, this is addressed by optimizing the index assignment. What we want is to ensure that two neighboring codes encode similar information, so that if, for instance, a bit is flipped, this does not result in a catastrophic change of the information. Let me go into a bit more details about this. Here I show a very simple case where we want to encode two-dimensional data on 4 bits. So that here, I assume that, with PQ, we don't split the two-dimensional vector into subvectors. We encode it directly, and we encode it with 16 centroids, okay? Here what we did was to assign each centroid randomly an index, okay? And here I show in a binary format the value of this index. And what we show in red are, the links between two centroids which are at a Hamming distance of 1, so the closest centroid, okay? And what you can see is that actually the structure of these red lines is pretty random, meaning that two vectors can be quite different in terms two centroids can be far away in the space, and still, they can be close in the Hamming space. Take the example, for instance, of this centroid, which is here, which is assigned 1, 0, 0, 0, and this centroid, which is here, there is only 1 bit of difference, so they are supposed to be close, but they're quite far away in the space. And again, it's normal that this can happen because we didn't make any effort to optimize the assignment. What I will show is that if we learn a proper assignment of the centroid indices, we can end up with such a structure which is much more regular, and where close centroid in the original space are also close in the Hamming space. So just to go back to my previous example, if I could interpret my codes as PQ code and as binary code, then I would have solved my problem. I have a query, I encode it, and then I loop over all my database items, and then I compute the Hamming distance between my query and my database item. If it's below a threshold, then I compute the Hamming distance. Okay? I still have my two-stage comparison, but because I use the same codes for the binary and PQ representation, I don't incur any memory increase. Now the question is, how do we learn a permutation such that the Hamming distance between indices reflects the distance between the centroid? We do so by optimizing this function. So we learn a permutation of the indices such that the Hamming distance between two permuted indices approximates the distance d between two centroids Ci and Cj. And of course, this is optimized over all pairs of centroids. We also have to add some terms. Typically, here we add a monotonous linear function to correct for the scale, because the Hamming distance is between two d-dimensional binary vectors is somewhere between 0 and d, while the distance between the centroids can be anything between 0 and infinity. And typically also we add a weighting factor to favor nearby centroids. This reflects the fact that we are especially keen on doing a good job at approximating the distance between close centroids, not between very far away centroids, because anyway, these codes are used, the binary interpretation is used just as a first filtering stage to discard those points which are very far away in the space. This is the objective function. How do we optimize it? We use simulated annealing. We start with a random permutation of our indices. Then we try to swap two entries in the permutation. If it decreases our objective, which is good, then we perform the swap with a given probability. If not, we don't perform the swap. And basically the message is that this you can learn really in a few seconds, and anyway it's an offline process, so it doesn't come with any cost, or very little additional cost with respect to PQ. What you can see here is as the number of iterations of our process increases, you see in red the objective function which we are trying to minimize, and as it decreases, it actually increases the real objective we're interested in, which is like the recall at 1 or recall at 100, which is like how many of the correct nearest neighbors we're indeed retrieving. So what I show here is the result of this index assignment. Sorry. So here we show the Hamming distance on the y-axis as a function of the true distance between random data points. And on the left, I show the case when there is no optimization. And so there is little correlation between the Hamming distance, between the PQ indices and the true indices. And this is not surprising, because again, we did not do anything to have this property. Here what I show is the correlation between the PQ distance and the true distance. And as expected, there is a very strong correlation. I say as expected because we know that the PQ distance is a good estimator of the Euclidean distance. And on the right, I show the Hamming distance as a function of the true distance in the case of Polysemous codes. So after we've optimized the assignment. And of course, the correlation is not quite as strong as in the PQ case, which isn't surprising. But on the other hand, it's significantly better than when we do not perform any optimization. So let me show you some results now. So the first results I will show are on a fairly small database of 1 million sieved vectors. For those of you who are not necessarily familiar with the computer vision field, sieve vectors were the standard descriptor for small image patches before the deep area. So here, we perform an exhaustive comparison using 16 bytes descriptors. What we show on this figure is the search time in milliseconds per query, the lower the better, as a function of the nearest neighbor precision, the higher the better. So really where you want to be is, in the, bottom right quadrant here. The two gray points here and here correspond to two baselines. This is the binary baseline, ITQ, and this is a PQ baseline. And what you show is exactly what I explained at the beginning of this talk, that ITQ, for 16 given number of bytes, provide a much lower accuracy than PQ, but on the other hand, it's much faster, okay? And what we show in blue with the crosses are the results of the Polysemous approach. So why do we have like a whole line? It's because, here in our two-stage filtering approach, we can vary, we can vary the threshold, okay? So here, what we show are the results for different thresholds. And what you can see is that there exist thresholds, which offer an excellent compromise, where basically we have the accuracy of PQ, and also we have the speed of ITQ, or very close to, like with a threshold of 42 to 646 bits. So that's exactly what we wanted to obtain. So what I'm showing now are results on larger scale databases, okay? On these larger scale databases, the comparison is a little bit more involved. Why? So here we have close to 100 million descriptors. They are CNN descriptors. They are the output of the AlexNet. And we compress them, they're 4,000 dimensional, and we compress them on 16 bytes. And on such large data set, even like exhaustive comparison with a Hamming distance is not possible. So typically what you do is some form of hashing, of inverted file structure, where you assign first your descriptors to different buckets, and then you perform the comparison with the database item only within the same bucket. So first assign to a bucket, then perform exhaustive Hamming comparison in this bucket, and then refine with PQ only for the closest items. So all the gray points, they are different, PQ results with a different number of buckets, 256, 64, 16, etc. So there are different compromises. And in blue, you have the result with the Polysemous approach for the different number of buckets. Again, you want to be in the bottom right quadrants. And what you can see is that, with the PQ without Polysemous, you get a certain compromise with a different number of buckets. And if you take the envelope of the Polysemous approach, you will see that you can actually get better compromises, okay? We also ran experiments on what is referred to the big ANN benchmark, which is, to our knowledge, the largest academic benchmark for large-scale indexing with 1 billion vectors. And compared to the state of the art, we report a 2.5 speed up with our Polysemous approach. Now we can do large-scale indexing in a very efficient manner. How can we use it in practice? So I'll show an application to the construction of KNN graphs, which is a nice possible way to navigate through a very large collection of images. So here for this experiment, what we used is again the Flickr 100 million dataset, which is a public dataset of Creative Commons images. We describe them with AlexNet deep descriptors. So the descriptors are 4,000 dimensional. Then typically we do a PCA to reduce the dimensionality, and then we encode them on 32 bytes. And in this case, we use like 4,000 buckets for very high performance indexing. So when we want to compute the KNN graph, what we do is in turn, each of the 100 million images is used as a query, and we want to compute the 100 nearest neighbor. So actually, this can be done, on a single CPU in less than a day, which I think is quite impressive and is really like well above the state of the art. Of course, this does not include the time it takes to compute the CNN descriptors themselves, okay? So what we show here is like for different queries, for instance, the closest neighbors according to our 100 nearest neighbor computation, and what you can see is that it's very consistent. Like, if you have a building, you retrieve images of the same building or very similar buildings. If you have a plant, you will retrieve similar plants, etc. So an application, is to compute the graph modes, which means, basically saying where the data clusters in our graph to discover some trends or, what people are most interested in. One way to do this is to interpret your graph as a Markov model, so a random walk where, at any given node, you can go to all the 100 nearest neighbor nodes, and in this way, go through the graph, okay? And of course, if you have a node which is connected to many other nodes, then certainly, it indicates that there is a very dense area here, that it's an area of high interest. So how do you do this? Basically, you compute the stationary distribution. It means that if you do a random walk for a very long time, what is expected probability you'll end up is in a node. And the higher the probability, the more connected is this node, and this means that the more likely it is to correspond to like a dense cluster of images. So, like to compute the stationary distribution, typically you start from, like a random vector, and you multiply this vector multiple times by your sparse k-nearest neighbor matrix. To reach convergence, typically we would do 200 iterations at the cost of 30 seconds per iteration, which is very reasonable. And so the nodes are the local maximum of the modes are the local maximum of the nodes. And you can see here the type of modes that we obtain. We have discovered, that of course people are very much interested in monuments. You have different, Eiffel Tower, Petra, Eiffel Tower under different conditions. You have textures. You have cats and babies, which is what many people are interested in posting on the internet. And also, flowers, plant, or, your favorite picture of your cappuccino, okay? So this technique can give you a quick idea of, like what, what are the typical clusters in your data set. Another application is actually to find, passes in your graph. So since almost all our images are connected, we can find a path between pairs of images, which provides a morphing from one image to another. Then which path should you compute? You can compute the shortest path, minimize the sum of distances, or minimize max of distances, known as a min-max distance. In our experiments, neither made much of a difference. And then whatever distance you have, you can use Dijkstra to compute the shortest path between your nodes. So what I will show is a set of examples. Here the goal is to go from this image to this image. And this represents, the set of nodes which are traversed to go from one to the other. And you can see that there is, a nice continuous transformation of both, shape and color. Same thing here, going from, a lion to a cheetah. Again, you go through actually, quite a smooth path. And what you can see is that actually the number of images you have to go through is much smaller. So the images are quite close. Same thing, how do you morph a dog into a cat? well, it seems that the transition is done through chihuahuas, which might not be such a big surprise. And then this is quite interesting, morphing, like an object into another view of the same object. And what you can see here is that you have like a very meaningful path where you start first, like zooming, and then, like maybe, like tilting your camera or something like this. And then, of course, you can try to find the path between different objects, and like going from flowers to Golden Gate. You have to go through this like some somewhat abstract structures, and sometimes you even take some very non-trivial and non-intuitive passes. Like if you want to go from a peacock to a cat, then you go through football players, maps, like these eye structures and babies, which is not the most intuitive. So, of course, the more images you have, this was with 100 million images, the more images you have, if we went to like 1 billion or even, larger, like 100 billion, then actually it would be easier and easier to find, like a meaningful path and a continuous morphing from one to the other. Okay? So that concludes my talk. Thank you very much for your attention. If you have any question, I think we have a few minutes left for those. If you'd prefer asking me the questions offline, feel free to come and see me either at the end of this talk or later during the day. I spend most of the day here. And also, if you're interested in career opportunities at Never Labs Europe, don't hesitate also to come and ask. We have many openings. It's really a great place, and I should have put some pictures. We have a great team, a great environment. We are surrounded by mountains. If you're interested in careers with us, please let us know. Thank you very much.